Good morning, ladies and gentlemen. My name is Mario Celli from UNICAL in Brea, California. And to the left is Professor Ray Anthony of the Chemical Engineering Department of Texas A&M. We are the co-chairman of the symposium. I have a few announcements to make. First, I'd like to recognize in the back the two session helpers. They are True Nguyen Yen from University of Maryland and Eva Mans from Howard University. They are both third-year graduate chemical engineer students, undergraduate students. There are some changes to the program, as you can imagine. Noticeably is a withdrawal of paper number 68D. There will be other changes that we are going to bring to your attention in due time as we go along. The symposium has one invited speaker, and the invited speaker this morning is Dr. Chianelli. Russ obtained his BS in chemistry in 1970 from the Polytechnic Institute of New York, and from the Polytechnic Institute of New York obtained his PhD in 1974 in solid-state chemistry. Even then, Russ was so good that Exxon could not wait for him to get his PhD to recruit him, so that he joined Exxon in 1973. Russ is the author to about 70 papers and about 35 patents. But I really think that his claim to distinction rests on his contribution of fundamental catalysis by transition metal sulfide, particularly noble metal sulfide. Russ is now head of a catalytic material group, which by design is an interdisciplinary group dedicated to the study of pathway in kinetics, to the study of solid synthesis, and to the study of solid characterization. The title of Russ' lecture is Structure-Function Relation in Transition Metal Sulfide Catalyst. The co-author of the paper is M. Daji. Please let us welcome Dr. Chianelli.
Thank you, Mario, for those very kind introduction. And it's a pleasure for me to be here giving this talk. The symposium looks very exciting. It seems that this area, which is lying somewhat dormant industrial for years, is coming to life for a number of reasons that I hope to be able to tell you about. May I have the first slide? By way of introducing the symposium, I would like to tell you that the sulfide catalysts have been important for many years. I'm sure that many of you know that. But the reason is that after World War I, the catalysts were actually discovered for coal liquids hydrotreating when people tried to do metal catalysis and the sulfides came out. And of course, we all know the story of the hydrodesulfurization, hydrodenitrogenation catalysts that emerged in this country after World War II. In the recent past, the interest has dwindled a little bit because we had catalysts that could take care of the light crudes that most refineries dealt with. But I don't think I have to tell this audience that as the environmental restrictions become more severe, the sulfide catalysts are again becoming quite interesting. But there are other reasons that they will be more important in the future that I think you should keep in mind. The feedstocks are getting dirtier. The catalysts that we have today are not capable of taking care of nitrogen and converting these heavier feeds. In addition to that, the sulfide catalysts are quite versatile. I think people are used to thinking of them as hydrotreating catalysts, don't recognize that they do many other reactions. In the 50s, for example, before noble metal reforming, the catalysts used were basically sulfide catalysts, and they would reform sour feeds. Recently, I think some of you may know that Dow and Carbide have announced that they are using sulfides for alcohol synthesis from CO and hydrogen. That's another example of how you're going to hear more and more about these catalysts. And what I'd like to tell you today is a little bit about some of the work that we've done and others have done to put some underpinning under the way in which these catalysts catalyze these reactions. And everything I'm going to talk about in the next few minutes, though directed primarily at hydrotreating reactions, since the structures and materials are the same, the principles ought to be, we should be able to apply them to some of these newer areas. Now, this defines the problem a little bit that a lot of people will be talking about today. Molybdenum disulfide is the stable state of the common hydrotreating catalyst. And as you'll see in the talk, if you want to understand how these catalysts work, you must start off knowing something about what the stable state is. The second point I'd like to make is that the promotion effect, which you're all familiar with, it involves in at least these two forms of stable states of the sulfides in the catalyst, and that the promotion effect can be completely described in terms of those stable states and their interactions. I say that because the catalyst that we all use is a cobalt molybdenum on alumina catalyst, and I think that though we will have some controversy about this, you can think of the alumina as something that disperses the stable states of the catalyst and that can add other functions like acidity, as some of the talks will go through. But basically, the promotion effect is contained in these two phases here. Now, in this particular talk, what I would like to do is to lay the basis by trying to answer some simple questions. They're not so simple, but some basic questions. What simple transition metal sulfides are most active for a given reaction? What is the basis for their activity? What is the relation of promoted systems to the simple systems? I'd like to just very briefly tell you about a unified electronic theory which relates all these solids together and forms a basis for understanding the industrial catalyst. And finally, to talk a little bit about some recent studies on microcrystallites, because in my opinion, one of the most difficult problems that remains to be solved in this field is based upon the problem that the dispersion of the commercial catalyst is not understood. Despite what you read in the literature, I don't think we really know what it is. And so all the models that people present in the literature, in the absence of hard knowledge on that, become very confusing. So this microcrystallite work that I'll talk about is an attempt to understand the dispersion problem a little bit better. Now, another thing that I would like to emphasize in this talk is that the work that we're doing at Exxon that I'm presenting today is really an interdisciplinary approach to the problem, involving catalytic material science, pathways and kinetics, theory and characterization, with a goal to understand and control the relation between catalytic structure and function. I want to emphasize this point because I think as we go into the future, and many of the talks that you'll hear today will emphasize this point, you really can't understand or improve these catalysts unless if you're only doing pathways and kinetics, or if you're only doing material science without pathways and kinetics, you don't really understand what you're doing. And so you need to combine these efforts, and I think more of the work that you'll see in the future will do that. Now, in this interdisciplinary approach, what I would like to talk about initially is some catalyst unsupported transition metal sulfide catalysts prepared by some techniques that are in the literature, like uniform flux preparation, a model reaction, HDS of dibenzothiophene and declin at 350 degrees C and 450 psi. We have found that over the years that is very representative of molecules in real feeds. If you can do the desulfurization on this molecule under these conditions, you'll get a pretty good measure of what you can do in a real feed within certain limitations. Here is a description of the reactor that we have used for these studies, and I think that is published, so I won't belabor that any, except to say that most of the results that I'm talking about have been confirmed in flow systems and in real feeds. To start off again, these are the stable states. These are the materials that come out of the reactor under those conditions that are identified by X-ray diffraction. And I think that it's another important principle, as I said earlier, to identify those stable states. And so all of these catalysts were made, run in the reactor under conditions that I showed you previously. The catalysts are taken out of the reactor and identified by X-ray diffraction other methods. Now what I would like to point out about this particular set of structures here is that they're all quite different. That most of these are layered sulfides, like molybdenum sulfide, which I'll speak a bit about later. But ruthenium sulfide is a pyrite structure. Rhodium sulfide has a very different three-dimensional structure. And this was a surprise to us that when running these under reactive conditions, identifying the stable states, the structure was varying quite a bit. And yet, as we see in the next slide, let me reiterate that this is the model reaction before I get to the slide I was going to talk about. This is the model reaction, dibenzothiophenes under these conditions, and the activities I'm reported are really the total disappearance of DVT for this talk. I'd like to remind you that the selectivity of the reaction, these are the other products here, biphenyl, cyclohexylbenzene here are the primary products of the reaction. And this, I'm not going to speak about the selectivity, but there's a very nice shell paper, I think, immediately following mine that will talk about it. And this is also, I think they will tell you, related to the structure of the catalyst. But in this talk, we're just talking about total carbon-sulfur bond breaking and not the selectivity. But you need to keep in mind that there's another aspect there, the selectivity in its relation to structure. In any case, as I said before, the stable states, though they have very different structures, will give these very smooth periodic effects, which just show you the ability of these catalysts to do the reaction that I just showed you as a function of the periodic position. And in this particular normalization, you can see that the transition metals, ruthenium and osmium, are the most active. In another normalization, the results are essentially the same, whether rhodium may be higher than ruthenium. And you use different normalizations here because when you're comparing all of these different structures, the anisotropy in the structure tends to make surface area normalizations as unreliable as any other normalization. So when you're looking at trends, you really have to just consider them as trends and look for these very large, several orders of magnitude effects. Now, since this result was published, there are many other trends appearing in the literature. Here is one due to Marc Ledoux in Strasbourg. This is a supported trend. These are catalysts on silica for a thiophene reaction, and they're essentially the same results as I just showed you, except the peak in this case is at rhodium and iridium. I show this slide to indicate to you that there are many others that have confirmed this periodic effect, and also that the periodic effects hold on most non-interactive supports like silica and carbon. But to my knowledge, to this day, when you go onto alumina, which is a very interactive effect, these trends are masked. And so that's another problem, that when you're reading the literature and you're really interested in alumina and you're trying to relate the basic effects to what you're doing, you have to keep in mind that strongly interacting support will mask these effects. And again, this is related to the problem of understanding the dispersion on alumina that I alluded to before. And now the next slide will show very quickly another reaction we've done recently. It turns out I've shown you two HDS trends. There are another one by Jean-Pierre Barnel in Lille for toluene hydrogenation, which looks the same. And there are several others in the literature from the Dutch group on HDN that look very similar. This is one of our own on HDN plus HDS. And it simply shows you that when you're doing the HDS and HDN equivalent, and here what I'm doing is summing the carbon-nitrogen and carbon-sulfur total bond breaking activity. And the thing that I would like you to keep in mind is that as you can see, comparing them against the trend that I showed you before. The rate, the sum rate for these very active noble metals are essentially the same when you put nitrogen into the system. This is an entire other topic, the HDN here, which I don't have time for today. But I would like you to keep in mind that the electronic effect, what we call the electronic effect, meaning which metal you're using in the reaction, is really the most important thing that you can start off with when you're thinking about which metal you're going to choose to catalyze a reaction in a fundamental sense. And I realize that as soon as you see ruthenium, you say that's a lot of money, so factoring out the economic factor. And what does it really mean? Well, first of all, I've said several times that you need to understand what the stable states are. When the catalysts are unsupported, that's easy to do. When they're supported, it's much more difficult, as we'll see as the day goes on. The other thing is that structure plays a secondary role. And that really means that the primary thing that I would like you to keep in mind about these periodic trends is you really want to get the 4 and 5d electrons into the system. And that is a general principle which is somewhat new for sulfide catalysts, but has been one that has been well known in reforming and other forms of catalysis for many years. And that, furthermore, that the metal sulfur bond strength is ultimately what's going to be important at the surface of the catalyst. Now, we wanted to try to take these basic principles a little bit further, to say a little bit more about these electrons, and to build a basis for unifying all these solids into a picture which took into consideration these 4 and 5d electrons. And this is the work that our theorist Suzanne Harris did with me a few years ago. And these are the results of some calculations which I'll very quickly show you. We made an assumption that the electronic structure of the bulk sulfides is related to the catalysis. And the experimental data that I've shown you indicates that that is true. The question of why that should be true is another question. But if you make that assumption and use a technique which we call scattered X alpha calculations, it basically calculates the electronic structure of a hypothetical unit like this in an octahedral configuration where the metal is titanium to nickel or zirconium to palladium. In this particular case, as you said, since structure is of secondary importance, we really want to focus on general electronic trends, and you do these calculations, and what you get is a set of molecular orbital diagrams like this, and you begin to fill them up with electrons. And as you do that, you can generate certain information about the electrons. Listen on this side of the slide over here, which I'm having a little trouble focusing, but anyway. You get the d orbital occupations, the metal, something about the metal-sulfur covalency in each one of these levels by how the sulfur P's and the metal D's mix. You can tell something about the covalency. And eventually, from all of this information, something about the relative metal-sulfur covalent bond strength. And as you do the calculations and get them across the periodic trends, you begin to look at them, how these orbitals are filling, the properties of the electrons in the orbitals, and you identify some factors that seem to be important in the sense that they are related to the activity trends that I've just shown you. And those factors are shown in this slide, and I am going through this very rapidly in the sense that I've left a lot of details out, which is in the paper and literature. But basically, when you look at these trends, you find two things. That the number of d electrons in the highest filled energy level are very important to determining which catalysts are most active. And secondly, that the relative covalent bond strength of the metal-sulfur bond is also a factor which is important. And you get this by doing your sums and differences in the antibonding and bonding orbitals as you would if you were anybody that was doing this would recognize that. And what we did was to combine these two factors into what we call an activity parameter And the activity parameter is the simplest form, which contains the essential factors found to influence activity. And here is a result showing experimental points here and the calculated points for the first and second row transition series that we've calculated. We have on the left here the activity parameter, and on the right here scaled appropriately the HDS activity that I've shown you before. And you can see that that the most active catalysts have this optimum metal-sulfur covalent bond strength. Up here I'm showing ruthenium as an example. And also the maximum occupancy of the highest energy-filled levels. The metal d orbitals that are the ones that are on the top of this whole series, the last electrons, if you will, that go into the system, the property and numbers of those are the things that correlate best to activity. So basically, any catalyst that you're making for this reaction and the many related reactions, if you were able to do any catalyst design, you would maximize the number of 4 and 5d electrons in those orbitals. And I think that some of the talks you'll hear later, talk by Glenn Schrader, talking about some other ways of putting together these metals, some very exciting results, and a talk from Unical by Simpson about some yet other ways of putting together the different transition metals will ultimately be maximizing the property that I'm talking about here. In any case, this theory and this idea that these electrons are important, in my view, is really the most important fundamental point in understanding catalysts by these metals. Now, having said that structure is of secondary importance, for the industrial catalyst molybdenum based on molybdenum disulfide, structure, as I'd like to show you in the next part of the talk, comes back in a very important way. And we start off that section by attempting to answer the question which I raised before. What is the relation between the bulk electrons? After all, the electrons are in the solid, and the catalysis is going on the surface. So can we suggest a relation between those bulk electrons and the electrons on the surface that are actually doing the catalysis? And I'd like to begin trying to answer that question in the following way. This is the XPS of a molybdenum sulfide catalyst, and when we do the theory, we try to measure some property like XPS, because one of the points that I glossed over here was molybdenum sulfide is in fact not octahedral, which is the calculation we did. It is trigonal prismatic. So when you're doing each one of the calculations, you'll extend the cluster, and you do the proper coordination, and then you compare the results here by putting the orbitals, scaling the orbitals on top of the XPS, and assigning them to see how well you're doing. And so this is the orbital that I've been talking about as being most important, the molybdenum 4d orbital. In molybdenum disulfide, there are 2 electrons here. And I've said that the character and type of the electrons that are here in the highest filled orbitals are the ones that are important for the catalysis. Now, by various techniques, if you begin to make molybdenum sulfides of higher and higher surface area or edge area, you find an additional density of states right here that goes as the surface area, or as I will say in a few minutes, the edge area of the MOS2. And so those electrons, which you can measure by UPS or other ways, and maybe those are also the electrons that you're measuring your chemisorption with, which is another way of measuring dispersion, are the ones that are important catalytically, and their properties are determined by the electrons that lie just below them. So in effect, one way of looking at the answer to this question is that the bulk electronic structure acts as an underlying electronic support, if you will, for the important electrons that are on the surface. And therefore, it's obvious, as I'll show you later, that the important electrons are related to the bulk electrons because they arise from the bulk electrons. Physicists are very unhappy when I make that statement, but I think it's one that is quite illustrative of what we're doing. Now, in addition to that, it turns out that another thing that's very important about molybdenum sulfide is the anisotropy of the structure, which I'm sure I don't have to describe to many of you. Here's a picture of the structure. It's a sandwich compound. These are the sulfurs here, and these red balls here are the molybdenum. And the essential point is it's a very anisotropic material. Many studies, our own included, have shown that these surfaces here, basal planes we call them, basically don't absorb anything, don't do any of the catalysis, so they're inert. And it is these terminuses here where we have these active bonds that the catalysis goes on in these atoms that are on these surfaces. And I think the evidence in the literature and many of the talks you hear today, that point is generally agreed upon. But the anisotropy of the structure has some other consequences. One of them being that it is very difficult to make surface area correlations or chem-absorption correlations because of this large amount of surface area that doesn't contribute to the catalytic activity. And therefore, this is a summary of what I've just said, and the crucial point that I'd like to make here is that the measurement of the edge area of these catalysts, whether they're supported or unsupported, becomes the crucial issue in understanding how they're doing the catalysis and in understanding how to make them better. And there's this problem, which I think is one that is not well solved in the literature, that when you're working with a supported catalyst, you do not know really what the edge area is, and therefore all models that you're looking at are questionable. And if there's one thing I'd like to leave you with, and I think you'll hear from other speakers, is that the models that are in the literature right now of how these catalysts work are all very questionable, and primarily, in my view, because of this lack of information about what the dispersion of the catalyst is. Give you one example of that. This is what a real catalyst looks like. These are large sheets of molybdenum sulfide, which are about 2,000 angstroms across. The total surface area of the system will be about 25 meters squared per gram. Here's another much higher surface area of molybdenum sulfide, whose surface area will be about 200 meters squared per gram. If you were to look at these closely, you'd see some lines here, and you see some lines here, and so on. These are presumably the edge planes, and you can imagine, because of this anisotropic structure, very highly folded sheets. And the sheets can be small or they can be large, and they will have very different edge areas. But many of the things, physical properties that you measure, will look just alike. And I'd like to give you one example here. This is some XAS work that we had done on MOS2, just like I showed you in the previous slide, and another material which is a chain material, amorphous chain material, MOS3. And the basic point is that in the literature, almost all of the measurements of dispersion based upon, on supported catalysts particularly, are based upon analysis of XAS data like that. The usual assumption that you would make in metal catalysts is that you can get by fitting this peak here, which in molybdenum sulfide is a metal-metal distance, due to the metal-metals, that by fitting that peak you can get the nearest neighbors out of coordination number out of that data. And therefore, in three-dimensional structure, you will assume that the nearest neighbor coordination number is related to the crystallite size. And you'll back calculate out the crystallite size from that information. And in fact, because of the anisotropy and folding and so on, there's an additional component in MOS2 which causes this peak to attenuate, and that is disorder. And that is almost never taken into consideration when the XAFs are analyzed. And I think we'll hear more about that controversial subject in the papers that follow mine. But I think it's very important for everybody to keep in mind that just because somebody says crystallite size of MOS2 is such and the model is such based upon that, there's more to it than that. And in the final part of the talk, what I would like to begin to address is what can we do about measuring this edge area, what types of techniques can be developed which will build us an understanding of what an edge area of MOS2 is and how promoters and molecules interact with those edges. Now, as I've said, there are many techniques that people have used to do that. We ourselves used to use oxygen chemisorption or some chemisorption techniques. And I think anybody that's worked with these systems recognizes the problems that are inherent in those techniques. We have used XPS and UPS, and even there they're not very sensitive to measuring this edge area. And Charlie Roxlow in our laboratory developed a technique. He didn't develop the technique, he developed the technique as applied to this problem, which we call photodeflection spectroscopy. It's basically a way of measuring optical absorption on very black powders. And the information that's generated is very equivalent to a reflection spectroscopy or some other visible optical absorption spectroscopy, if you can get it. And the technique which we published and is in the paper I won't go into, but basically it allows you to measure these optical properties on black powders, which, as you know, all these catalysts are. And it turns out that with the photodeflection spectroscopy, this is the valence band, and I've switched over to band language here, but basically these are just the molecular orbitals I've shown you before. So the electrons we're interested in are the electrons that are here at the top of that valence band, and you're measuring with this PDS a transition from here up into the conduction band. And as you'll see later, I've already indicated, but this tail up here on top, these are the electrons that ride on the bulk electronic structure that I was talking about before. These are the ones you're really trying to get information about because they're the catalytically important ones. Other techniques like UPS and so on, they look at the same information, but they take the electrons to the continuum, and therefore they're not very sensitive techniques. So this optical technique is very sensitive, and the other thing that we needed to be able to do this correctly is some catalysts and samples that have well-defined edge areas. As I said, the normalization of the catalysts, NOS2 type catalysts, are very difficult. So we were using these materials called microcrystallites. We're showing a large set of microcrystallites and a small set of microcrystallites here. These are MOS2 platelets. This is the basal plane. You can see a very nicely defined edge area here. You can measure the thickness and so on. Everything is geometrically determined from the micrographs. And you go through some statistical analysis of these platelets, and you come up with a site density for the edges, which you're not relying on any other physical technique to measure. In this case, the large platelets have 7 times 10 to the 16th sites per gram of NOS2. And the small platelets have a much higher edge area, 10 to the 17th edge sites per gram. The average size here you see is about 1 micron, here about 100 microns. Now the other point is after making these well-defined catalysts, you can measure the catalytic activity in a model reaction, have done so in the dibenzothiophene reaction, so you get a real hard turnover number per edge site for DBT, and that then becomes basically a fundamental constant which you can input into all of your other catalysts to determine the edge area. In addition to that, you can apply to these materials the photodeflection spectroscopy that I mentioned before. And so here's an example of the data that you get. This is an absorption spectra of a single crystal. Here is what we call the band edge. Here are the large platelets, the small platelets, and a real catalyst powder. Real catalyst, I mean by real catalyst, some of the platelets, they're real catalyst. The one that we might actually use up here. And when you get that information and analyze it, you find that the defects in this region here, if you take a particular point, are going as the edge area of the catalyst. Remember I said before when I showed you the valence band diagram that this tail up there was what was important. And this technique of absorption in this region is basically counting those electrons that are doing the catalysis for you. And that's what we really want here, is a way to count the electrons that are hanging off the edge and doing the catalysis, and that's what the technique gives you. And we've done this fairly extensively on a number of real catalysts, model catalysts, and so on. You come out for these reactions with a fundamental turnover number, which you can then begin to use to relate and normalize all the other data that you have. You find that the edge sites are identical on single crystalline powders and supporting catalysts and so on. The edge area and edge density can be determined using the turnover frequency in the cases of crystallites where you can't do what we said we did with the crystallites where the edge area is determined. So you can basically use this number to put into any catalyst that you're using in that reaction. And in principle, if we all cross-correlated other reactions and conditions that we're using, we could agree upon what this number is, and some of the ambiguities, many ambiguities in the literature would be lifted with this knowledge. Just a word about oxygen chemisorption. When you begin to do this, you find that the oxygen chemisorption that's reported in the literature in many places, our own included, gives you a turnover number which is about 10 times smaller. And the reason for that is that the oxygen is corrosively going into the edge. And it depends upon the condition that you're going. The higher the temperature, the more that's going in. The lower the temperature, the less. But the oxygen chemisorption everybody uses in these MOS2 systems is one that's proportional to the edge area, but is not counting correctly the atoms that are actually on the edge because of this corrosive effect. So the correlations, which you see in the literature, are correct, but they're just correlations. They're not giving you real edge site density numbers. And the other thing I'd like to say is, okay, we can measure this edge site density. I'd just like to say a word about what this means. As what we're trying to do here is build a picture toward the quote-unquote active site. And I'm showing you here a really specially prepared sample of MOS2. These are all the layers, with some drawn in here for guidance of the eye. These layers are 6 angstroms apart, approximately. You make a sample like that, knowing that the edge area is important, you can begin to do some things like measure the XPS. Here is the XPS measured by John Gland and his workers on what we call a textured MOS2, which is what I've just shown you, compared with a single crystal. The basic point I want to make is that you find this additional set of peaks against a single crystal. And again, these are the electrons that I was talking about before, that are the defects created at the edge that are catalytically important. And when you look at that, in this particular case, you come to the conclusion that that looks most like molybdenum-3. So that in a, you can imagine that the edge sites on MOS2 actually are molybdenum-3. Now, John Horsley, who is now with Catalytica, did some calculations, X-alpha calculations, which are shown here. What he wanted to do was to calculate what the electronic structure of these various defects look like as you pull off first one, and then in 2 different ways 2 sulfur atoms from the basic molybdenum sulfide trigonal prism. And these would be formally, as a calculation show, molybdenum-3 type defects that are created. And what he was showing is that both the calculated cross-section, because from these calculations you can calculate this optical transition that we measured, so that what we call an error bar here shows you the predicted place that you, intensity of these, and the energy for these types of defects. In other words, where you would find them in the visible spectrum. And as you can see, these types of defects always fall quite well within the area where we're saying we've measured the edge defects that are important. And that's all I'd like to say about building a picture of the active site for this, is that we're having an indication that things that people would predict would be the active site on the edge of an MOS2 are giving us the right or predicted physical properties measurement in the right range. So we're getting to that picture there too. Now, up to this point, I haven't said anything about promotion. And I will conclude the talk by talking a little bit about the promotion problem, because everything I've said up to this point in the talk has been about a pure sulfide with no additional component in it. And in my view, in order to understand promotion effectively, you must build a base for understanding these molybdenum sulfide edge planes, because in the industrial catalyst that we use, molybdenum disulfide is the stable state. Although I hope that you remember the first part of the talk in which I said that at the first level you have to modify what you're saying about any particular structure. If you can find another stable state that doesn't involve edges, you have to start thinking about your basic electronic structure again. In any case, I'd like to make a few comments to close about the promotion system. Based upon what I've said, this is just a summary of the previous part of the talk, the points I'd like you to remember about molybdenum sulfide. Highly anisotropic, basal planes are inert, the important reactions take place at the edge planes. Disorder is a severe problem in understanding anything about these catalysts. Edge defects lie just above the highest occupied molecular orbital in the mid-gap, the important electrons that I talked about, and at the edge defects appear to be molybdenum like. Now, when we begin to talk about promotion, what I'd like to show you here are two model catalysts that are grown at high temperature. This is molybdenum sulfide. This is molybdenum sulfide doped with 1% cobalt. And these are the edge planes right here that we've been talking about. Now, the first thing you notice is that the crystal that has cobalt in it has a much higher stack height. These are much steeper edge planes. And that's interesting to a material scientist, because if you know something about the structure, you look at that and you say immediately, there's something here that's increasing the interaction in the third direction. The reason that these things don't stack up, it's very difficult to grow thick crystals, is that there just isn't any interaction in that third dimension that's very strong. So this is already telling you that the cobalt's in there somewhere. And I think you all know the literature going back to the work that Rudy Vorhoeven did at Shell many years ago, which indicated that cobalt or nickel was going to interact at the edges somehow with MOS2. And if you grow the crystal, you see indication of that. Furthermore, if you do some OJ mapping on the same crystals, and the OJ map basically tells you what elements are there, you find two things. You find this is actually an oxygen map. You can see that if you don't clean the crystal, you have oxygen all over the edges, and very little on the basal planes. It's another indication that your chemisorptions, your activity is at, your reactivity is at the edge planes. And more importantly, this is a cobalt map. And this shows you in a very nice way that the cobalt in these crystals is at the edges. And if you analyze these crystals in the middle somewhere, in the basal plane, you just don't find any cobalt. This is a chemical analysis on a microscale. It was done of those crystals by Jose Yacaman from the Institute of Physics in Mexico. And when you look at this analysis of those crystals, you find that the stoichiometry at the edge is something like that, which, as you all know, is the industrial, within the range of the right industrial promoter. And I think that the picture is much more complicated than that. But this is another way of emphasizing, this slide shows another way of emphasizing that the edge area is important. At zero cobalt in these, this is again the rate for HDS, you see that there are basically three samples here. You can't see it very well on this slide. But at zero cobalt, you would have three activities of pure molybdenum sulfide that vary according to the edge area. These catalysts that are indicated here, it's not important how they're made or anything, have progressively higher edge area. When you do that, treat them as if they were a support, and put cobalt on them, you get curves that look like this. And the basic message here is that it's a very simple point. The higher the edge area, the more effective the promoter. And so this is a picture which seems to me to bind at least some of the theories in the literature together. If you're above this curve, this point, let's say over here somewhere, or over here in this particular case, you're going to, if you X-ray or analyze it, see a lot of cobalt 9S8. If you're down in this area here, you're not going to see much, and here's where we get into the controversy about what is that stable state of that cobalt that interacts with the edge. So that I think if you read the literature with this kind of picture in mind, you can see that a lot of the theories in the literature turn out to be really saying the same thing. That at high loadings you'll see this extra phase. At low loadings you won't see this extra phase. But the really important thing is what happens either when the phase is present at the boundary where they contact, which would be something that Bernie Delmont would tell you the phases have to be in contact. Or if this phase isn't present, the interface between the cobalt and the molybdenum sulfide is really the thing that we need to focus on as the origin of the promoted effect. And because of the dispersion problems and various other problems, this question is not clear in the literature right now. We're at a period of time now where the controversy is welling up again about what this structure is. I would like to make some suggestions for argument's sake. Having known this information a number of years ago, we proposed that the way these catalysts work is, in effect, to have a vacancy bound between cobalt and molybdenum. What this will do for you is to average the property of those vacancies. And so we went back to our X-alpha calculation with the same principles that I told you before. And we imagined that there was something like this at the edge. Okay, molybdenum sulfide sharing sulfur with a metal. And then we do the calculation with these various metals. Two of them are known promoters. When we do that, we look again at the electrons in the highest filled orbitals. We find that the cobalt to nickel promotion arises from an increase of the factor and the number of electrons on the molybdenum. Just as we showed in the simple sulfides, that being important, when you put cobalt in something like this, you get that increase of the electrons on molybdenum, and the same for nickel. Copper, which actually poisons the catalyst when it's in the DBT reactor, actually pulls the electrons away from those orbitals. Again, in agreement with the theory. And these other metals are basically neutral. Okay, and so we would generate a modified activity parameter. Basically, the other factor I talked about, covalency, is roughly stays the same, so it's just these counting. And here again is a comparison of the activity parameter shown on this slide against some measurements made in DBT, again showing rough quantitative trend results using this picture of electron transfer at these special sites on the edge. This reiterates what I said before. The cobalt donates electrons, increases the number here, and that's a promoter, and the copper does the opposite. It takes electrons away, and it's a poison. The other metals, basically, if you look at the calculation, don't do anything. And so that's a basis for an electronic origin of promotion. And since we published, you see many things in the literature where this theory is taken and interpreted in different ways. That this electron withdrawing or adding properties, one group will say, that's right, but what it does in effect is enable you to increase the dispersion of cobalt, or so on, be interpreted in different ways. So I'd like to remind you that it is just that, it's an electronic theory, which brings together promoted systems, poisons, and simple sulfides. But there's another set of steps that have to be taken from that to understand exactly what the promotion effect is. Nevertheless, it has led us, and this would be the final slides here, to try to synthesize. This is work done by Ed Stiefel at Exxon and his group. And this very funny looking molecule looks like got legs or something like that. So it's actually the product between this molecule, which contains molybdenum, which they call a synthon, meaning that they started using it as a basic building block and do a lot of chemistry. They treat that with cobalt carbonyl and acetonitrile, and they get this thing. Okay. And they get this called a thiocubane. It's a general class of clusters that have the metals in tetrahedral relation like this. And you can see in this molecule, cobalt fragment of cobalt carbonyl with the CO bound is inserted, basically here to give you that cube, and the molybdenum is here. Now, it turns out that in parallel studies, we have used cobalt carbonyl as a promoter on some of these crystallites that I talked about before. It's a very effective promoter, and you can measure the activity. So the suggestion then is that this is a model of the structural electronic interaction which occurs at the edge of an MOS2 crystallite. Now, the interesting thing about this particular model is that what it does is open up these sites on the molybdenum here so that the solvent molecule actually binds to the molybdenum, which it will not do in this molecule. Okay? So it's a suggestion that this is another way which cobalt interacting in the way I said before creates a site of molybdenum. Now, having shown a very specific model here with all of the questions about XAFs and so on, which I'm not going to answer today, I'd like to say that there are many other molecular models of this type that are being looked at. I don't know whether this is the right one, but I think it's interesting that we can begin to get close with some of these inorganic molecules. This is basically the same molecule again, and I just wanted to show you that the electronic formulation shown on the bottom here, cobalt-2 and molybdenum-3, is exactly the one that I was talking about before in theory. However, the inorganic chemist will say that this formulation is, in reality, equally as valid as this one. And in this case, it has cobalt-0 on the molybdenum-5 molecule. Now, I would be very hesitant to believe that molybdenum-5 will exist in the reactor, but cobalt-0 can exist in the reactor. And I think the basic point is that when we begin to talk about the oxidation states of these couples, what we're really saying is that they're all lying very closely together, and that they can shunt electrons back and forth when they get in this configuration very easily between these closely lying states. And that really is ultimately, whatever the ultimate structure is, or the ultimate assignment of the electrons, that's what's really important. The ability to move these electrons back and forth in a catalytically promoted system. And so I leave by saying there's still many questions in this system, and try to give you a feeling for some of what I think are the important fundamental underpinnings that we have to look at all the work in view of that. And to say thank you for inviting me, and welcome any questions.
Next paper is a contribution from Shell Development Company in Houston, Texas. The title of the paper is Investigation into the stacking of molybdenum disulfide layers in hydrotreated cathodes.